Hello everyone, welcome to our Chemistry 3-4 Unit 4 Head Start lecture today. As you can see, today we're doing a recording. It's a little bit different. Things are sort of changing up. For those of you in the sort of premiere, like live stream, it's not really a live stream, but premiere of the recording, I'll be there in the chat, so you'll be able to see me there in the chat. I've probably said hi by now, so hello to sort of future me. Beyond that, for those of you who are not watching the premiere, you'll be able to access this recording, and those who are at the premiere, you'll be able to access this recording afterwards. If you have any questions for those at the premiere, please ask them in the chat. I'll answer them. The chat will still be accessible afterwards, so those who are not watching the premiere and who are watching it later on, please feel free to look through the chat that will already be there. You won't be able to ask any questions because I won't be there, but you'll be able to read what's already been asked, and hopefully the questions you have already been asked, and therefore you don't really need to ask them again. Otherwise, the lecture today will go for 2 hours, and as I said, any questions, please use that chat function. Whoops, I need to do that. Easy. All right, so first of all, just a big welcome. So today, obviously, I'm Josh, and I'm representing ATAR Notes. So ATAR Notes have been around for a very long time. I think it started in about 2007. Lots and lots of free resources. And they've been offering free lectures since about 2015. I remember attending these in both 2017 and 2018, so my year 11 and my year 12. It's a very, very long time ago, and I was already attending these. They used to be back in person, but then obviously COVID changed the landscape and everything that we do. We offer some free resources still. So as you can see, we've got sort of study notes. You're at one of the lectures here. We have discussions. We have videos. There's lots of different things. Just head to the website and you can find it all there. What's really cool is that you sort of had access to lectures from like 3 years ago to today. And you have access to study notes and forums that have been going on for years. So really, really cool. You can get around that. And then we do have some paid resources. There'll be some promos down below, so please don't hesitate to sort of scroll down on the page and just have a look at those promos. But essentially, we have 3 different sort of paid programs. The first one is TuteSmart, who personally, that is who I work for, which is how I end up here today. So TuteSmart is our tutoring program. It's class-based, but there's also one-on-one tutoring, so there's a bit of both. Depends on what you like, and you can sort of get access to loads of tutors. So there's people like me, and there's also people that specialize in things like English, humanities, PE, maths, etc. We also have the study guides. I'm sure you've seen them before. There's loads of these around. And then there's also Ed Unlimited. What's really cool about Ed Unlimited is it's all of the study guides, the printed versions. It's all of those on like an online resource. So you can only access them through that resource. And what's really cool about it is it's like a monthly subscription. So you can get it for a little while, and then if you don't need it, you can sort of unsubscribe, and then if you feel like you need it again coming up to exams, you can subscribe again. That's sort of the cool thing about it. So who am I? So I'm Josh, and I have been tutoring here for just under 5 years. I've been tutoring since the start of 2019. I specialize in chemistry and further, and I do a little bit of biology on the side. I used to do a little bit of physics and a little bit of like UMAT, UCAT. Don't really do that anymore. I graduated in 2018. I used to be from Bendigo, so I graduated in 2018 with a 98 ATAR, and I had a raw 44 in chemistry. That's a bit about me. I have 2 pets at home. I now live in Melbourne because I study medicine at Monash. I'm currently at the Heart Hospital on Monash campus. But these are my 2 pets that I go home regularly to see. So we have Maya and my very chubby cat, Bella. So jumping in, this is how today is going to look. So we're going to do 60 minutes of each. We're going to do a bit of organic chem and then a bit of analytical chem. Now, what's sort of really important here is the organic chem we're probably going to spend more focus on, so it may go a little bit more than 60 minutes, and then the analytical chem may be a little bit less. The aim is to spend 60 on both, but everything's not perfect, so things may change. What you'll find is that this is all of sort of area study 1, of Unit 4. So we're not going to touch area study 2 of Unit 4. So we're not going to do any food chem. We're not really even going to finish analytical chem. I've only done like the basics of it. We're not going to go into super detail. And that's sort of important as well, just to know. So that's today. So we have sort of, as you can see here, we've got block 1, organic chem. We've got block 2, analytical chem. Easy. So what do you need to know? So unit 4 sort of looks like this. What's really important is that this is all area study 1, despite the fact we're going to break it up. We break it up into 2 parts. It is all area study 1. And as you can also see, it's way bigger than food chem. The one tiny section of food chem, which is area study 2, is smaller than both of the subsections of area study 1. So please be prepared that this is a big topic, organic chem and analytical chem, and it all sort of flows on from each other, which is nice, but it is a large topic and it makes up quite a large proportion of the exam. So it's really important that you know this stuff and you're comfortable with it heading into sort of, all of the exams and SACs and all of that. So we're not going to touch on food chem today. This is sort of the study design broken down into little sub bits. So we've sort of got the study design and sort of broken it down into little even smaller dot points. Please make sure that you still use the study design real dot points. And what's also really important is that you make sure you download the correct one. So there are 2 floating around at the moment. There's 2 because the study design is changing next year for year 12. It changed this year for year 11. So those of you who did year 11 last year, which is all of you, I'm assuming, who did 1, 2 last year, you will have done the old study design. You're doing 3, 4 this year, you're doing the old study design. Those people who are in sort of year 11 now and are doing 1, 2, they're doing a new study design in unit 1, 2, and a new study design in unit 3, 4. So it's sort of like a phased transition. So we're sort of in that in-between year. So really important that you make sure you download the old study design, the one for 2023. So it should be, I think it should look something like 2017 to 2022 / 2023. That's because it was meant to finish in 2022, but then they extended it by a year with COVID and everything that was going on. But they didn't extend it for year 11. So for you, it's that one there. Make sure you download that one. There are distinct and significant changes to the new study design, so make sure you don't download that one, because then you'll be looking at it going, what is this? There's stuff here I haven't looked at before. So topic 1, organic chem. So organic chem is actually pretty fun. I think organic chem is probably one of the better topics. So these are the things that we're sort of going to cover. We're not going to go into too much detail in the first 2. The first 2 are pretty much the basics. I think the last 2 are really the important ones. They're the things that make up the majority of this topic. So why should we care about organic chem? So this is sort of just a random thing, but do you like sort of the following things: going places further away than down the street, and having electricity that doesn't kill the earth, food, not dying, so things like paracetamol and penicillin. There are so many different sort of molecules that are important to life. They're important to how we work as a society, and all of these molecules fall under organic chem. Organic chem is essentially understanding how things work and what things look like. So on a molecular level, what do we look like? So what do all these molecules have in common? They're all organic molecules. So essentially we are going to be looking at organic molecules. We're not going to be looking at inorganic, which means that they're either created sort of artificially or they're not created within a living creature. Those are inorganic. We're not going to worry about them. Today we're only going to be looking at organic, and that's all you're going to look at for this topic. So organic chem is everywhere. What exactly is it? Organic chem is just the study of manipulation of molecules that are found in and produced by or related to living organisms. So we call these molecules organic molecules. Almost all organic molecules contain carbon and hydrogen. So this is not organic. So we're looking at a CO2. Here we're looking at organic molecules. I think our first one there is butane, and then we've got a far more complex molecule there that I don't know what it is. So these are all organic molecules. It's really important, so these ones on the right, it's really important you understand that organic molecules are going to contain carbon and hydrogen. That's just the basis of it. What's so cool about carbon? I'm sure you learned this in year 11, but just a quick refresher, carbon has 4 covalent bonds, and thus it's really useful because we can connect lots of things to it. It's the bonds that it does form are usually really stable as well. Therefore, it just makes it a very easy molecule to sort of manipulate and work with. And that's why organic sort of Compounds are formed with this because when organic compounds form, it's the exact same thing. They think of the exact same things as we do. They think, hey, what's going to be the most stable? What's going to be the best option? What's going to give me the best flexibility? It's going to be carbon. So carbon is essential to life as we know it. Carbon for millions of years, and then essentially millions of years of evolution. We had carbon around, we had water, other organic molecules, and essentially we ended up with life. So how do we classify organic molecules? Well, we can sort of think of it like flavors. Think of it like going and buying an ice cream. What are the different flavors that we have? So you've got all these different flavors here. How does this work? Well, we've got all of these different organic molecules, and they all fall under different categories. We have alkanes, alkenes, alkynes, halogens, amines, alcohols or alkanols, whichever one you want to use, ketones, aldehydes, esters, carboxylic acids, all of those things. So lots and lots of different names and functions, and we're going to discuss all of it today. So please don't worry if you're like, oh, what are you talking about? You're going through really complex things. We're all going to talk about it all today. So in chem lingo, we call all of these flavors different homologous series. So really important that you know what that refers to. A homologous series refers to sort of the different molecules within sort of one subsection. So for 3-4 chem, we need to know how to name molecules belonging to these homologous series, as well as the types of reactions they undergo. So a homologous series, essentially, this is the definition, a family of molecules that have similar chemical properties, differing only by the additional carbon and hydrogen atoms to extend the hydrocarbon chain. So this is an alkane homologous series. Why is it an alkane homologous series? Well, we have ane at the end. Ane refers to single bonds only, and in between our carbons here, we only have single bonds. So therefore, we refer to this as an alkane series. Hopefully this rings some bells from last year. So let's recap organic chemistry covered last year because it's important to know still for 3-4 chemistry. So we're going to start off with alkanes, alkenes, and alkynes. So this is just, we're going to go through each of the homologous series in their basics. So we're going to start with alkanes, alkenes, alkynes. So we're going to go into sort of naming chem first after that, and then we'll jump into functional groups and the other homologous series. So just want to go over just the basic group first, which is alkenes, alkynes, all of that. Then we're going to do some naming, and then we're going to jump straight into our functional groups, because functional groups is kind of the next step on. So we need to sort of know how to name before we jump into functional groups. So, alkanes. Alkanes have a general formula of CnH2n plus 2. Now, what does that mean? So, if I have 4 carbon molecules, so I have N equals 4, I say C4, if I'm an alkane, it has to be 2 times 4 plus 2 hydrogens. So it's going to be 2 times 4 is 8 plus 2 is 10. So that fits into my alkane series. Now, what if I had 8 carbons? Well, if I had N equals 8, I would have C8, H18. So think of it as like double plus 2. So you're going to have double the hydrogens plus 2. Now, that's the general formula. That's all single bonds. We refer to this as saturated. Really important that is what we refer to it as, saturated. Now, what does that mean? It means that it is completely full with bonds. There are no places where you could break a bond and add another bond in. So essentially, if I had an alkene, looks like this, I can break one of these bonds and then add an extra 2 bonds in. That's not saturated. Once you break the bond, it becomes saturated because there's no other places you can add bonds in. So in this case here, alkanes are always saturated. Now, alkenes, on the other hand, are unsaturated by the point we just talked about. They have a double bond somewhere. Now, alkenes will have a general formula of CnH2n. Now, this assumes, really important, this assumes that there is only one double bond. Because you might have a molecule that looks like this. And then here, you're going to have 1, 2, 1, 1, 1, 2. In this case here, you've got C4, H6. Now, that doesn't meet this rule because C4, H6 is not, N is 4, and then you've doubled it, you get 8, you don't get 6. That's because these general formula rules assume there's only one of the special bond. So in alkanes, there's obviously no special bond, so it doesn't matter. In alkenes, it assumes there is only one double bond. So as you can see here, there is only one double bond going on. So one double bond. These are unsaturated because, as you can see, there's potential to add 2 bonds here and remove 1 there. So it is unsaturated. Then alkynes, again, they're also unsaturated. These ones have a triple bond. So their general formula is CnHn take 2. And again, the general formula assumes that the triple bond only occurs once. Really, really important. The triple bond only occurs once. So there is no double triple bonds there. There's no two triple bonds or 3 triple bonds. There's only 1. So moving on to sort of naming, it's really important you remember this from last year. I'm sure you all remember it, but it is something you do need to know. You need to remember your IUPAC systematic naming all the way up to 8. So you've got meth, eth, prop, ut, pent, hex, hept, oct. So you've got 8 of them. So you do need to remember this. The reality is if you don't remember it, you need to find ways to remember it. You need to go through it as many times as you can and remember it. For me, I don't actually have a way. I don't have some like, jingle or acronym to remember it. I just remember it. It's something that once you see it enough, you're just going to remember it. And that's the reality of it. So if you don't know it now, you need to be continually using it and continually doing these questions to sort of build your knowledge on this. As you can see as well, there's multiple ways of sort of drawing out molecules, and this is just another quick point. You do need to, in Year 12, be able to draw all of your molecules in the 3 different forms that they want. So in last year, there was really only 2 forms. The 2 forms were semi-structural and structural. This year, there's 3. Semi-structural, skeletal, and structural. So this is what we refer to as semi-structural because you can sort of determine the structure from that, but it's not very clear. Structural is this one down here because it's very clear what the structure is here. It's very obvious what your structure is. It's drawn as the structure. And then skeletal sort of is referred to skeletal because it's kind of just looking at the spine of things. So as you can see here, this is skeletal. The cool thing about skeletal, and it's something that hopefully there'll be more questions on, I think I put another one in there. What you will see is that every corner or end that doesn't have something like another molecule drawn in there is a carbon. So this is a carbon, this is a carbon, this is a carbon, this is a carbon, and this is a carbon. So there are 5 carbons there. There is a double bond, to be made very clear by a double line. All the other ones are just normal bonds, and then there's hydrogens coming off. You don't draw the hydrogens in a skeletal structure, you assume that they're there. So each corner is a carbon, and the ends are carbon as well. So if I were to have ethane, for example, now ethane looks like this. This is ethane. To draw ethane, it's literally like this. That's ethane, according to a skeletal structure. That's where skeletal structures are not very useful. We don't generally use skeletal structures all that often in simple molecules. When it comes to complex molecules, skeletal structures are really, really common because they simplify it down. Skeletal structures are there to simplify it down. So when you have simple molecules like ethane, not that useful because, as you can see there, it's a bit of a mess. But when you have really complex structures, you can do it quite well. So here's just some examples of some molecules. As you can see here, they're all different. So we've got butane for the first one. We will have, I think, pent-2-ene for the second one. Yep. Now, why is it 2-ene? Because it's on the second bond. So bond 1, bond 2, bond 3, bond 4. Yeah. Now, that numbering is slightly different to our carbon numbering because if I'm going to number for carbons, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So there are 5 carbons, but there are only 4 bonds. So bonds are always 1 less because that's just the way it works, unless you're in like a ring. And then lastly here, we've got 1, 2, 3, 4, 5, 6, 7. So we've got hept, we've got an ene or an ine. Is it 7 actually? 1, 2, 3, 4, 5, 6, 7. Yep, so it's hept. We've got an ine, so it should be hept 1 ine. Actually says oct, 1, 2, 3, 4, 5, 6, 7. So that actually should be hept. I do apologize. I think I might have miscounted that when I was making this. But that's hept 1-ine because the bond is in the first spot. So this is the first of all of the bonds. So that's hept 1-ine. So naming simple hydrocarbons is easy, but what are the general steps to naming any organic compound? So let's go through the general steps. So the IUPAC naming convention, this is just the way that we name chemical molecules, because in science there's a couple of different ways of naming them. The IUPAC is the most common. You might also see it referred to as nomenclature. So nomenclature is this. Nomenclature, you'll see it referred to as that. Nomenclature just refers to the same thing, it's just the naming convention. So don't worry about that. So steps. These I think are the easiest sort of ways to go about it. So first of all, take a step back and just identify what is like, what type of molecule you got. What homologous series does this belong to? Does it only have single bonds? Well, it's going to be an alkane, but does it have functional groups? Well, if it's got functional groups, what functional group does it belong to? So sort of just figure out what are the main things there. 2, identify the longest carbon chain, and that will be, you know, your meth, eth, prop, etc. Pick the end closest to the first substituent or the one that has the highest priority. Now we'll talk about priorities later on, but don't worry about that. And when I say substituent, I mean like a functional group. Has it got a carboxylic acid? Has it got an alcohol? That's your first substituent. But also look at your priorities. Number down the longest chain, noting substituents and their positions, put the name together, etc. So we're going to go through that, don't worry. But essentially, you're going to have a prefix, the chain, and then a suffix. Now, what's really important is that the suffix is always the highest priority. People want to be suffixes. So suffixes is like, you know, your higher echelon in society. Your prefixes are not. They're your lower echelon. So people really want to be suffixes. So these functional groups really want to be suffixes, but not all of them can be, because the higher priority, the more likely you are to be a suffix. And we'll explain how that works. So as you can see here, we've got a molecule, and I'll go through naming this molecule. So it's given us both the skeletal and the structural. So it's a really good way of looking at how the skeletal and structural sort of line up. So we'll use the structural. Our longest chain is 1, 2, 3, 4, 5, 6. Now, I could have counted from this one. I could have counted from this one. It doesn't matter. It doesn't matter which one you're going to count from. It's all going to be the same. So we've got 6. So I'm going to say 1, 2, 3, 4, 5, 6. I don't need to worry about priorities because there's only one functional group or, you know, extra thing here, which is a side chain. They're both the same side chain, so that's why I said it's only one. So we've got a methyl and a methyl. They both come off the second carbon. Now, methyl is really interesting. As much as I said, you know, we really want to be a suffix and there's no other suffix here, so you'd assume methyl would be a suffix. There's actually no suffix for side chains. Side chains always go at the front. So no matter what, side chains are a prefix. So in this case here, they're at 2. So I'm going to say 2, 2. So when you have numbers, commas go between them. When you have a number to a letter or a letter to a number, it's a dash. So now I'm going to do dash. In this case, I've got 2. So the 2 ones I want you to remember are di and tri. So di equals 2, tri equals 3. Now, what does that mean? It means 2 times a functional group, or 3 times a functional group. So dimethyl in this case here. So this is going to be dimethyl, and this is going to be 1, 2, 3, 4, 5, 6. So it's going to be hex and then ane. Hexane. So this is 2,2-dimethylhexane. Really important, comma between the 2's, dash between the 2 and the D, because a letter and a number needs a dash, a number and a number needs a comma. I put the di there because it referred to being 2 methyl groups. It's important you also write 2, 2, because they're both at the second position. If it was 2 and 5, you'd write 2, 5, or 2 and 4, you put 2 and 4, or 3 and 4, 3 and 4. Doesn't really matter. It just needs to have both the numbers of where they are. So if it's tri and they're all at 3, which wouldn't be the case, it's impossible, but nonetheless, let's just say they're all at 3, you go 3, 3, 3 dimethyl, which is impossible, but just for context. So answer here, 2, 2 dimethyl. methylhexane, sorry. So what's really important here is that you also sort of know your other important rules. So substituents must be listed in alphabetical order. And it's really important that you ignore the prefixes for multiplicity. So in this case, what we're saying is that the prefixes need to go, so if you have multiple prefixes, so here we've got a molecule that's 1, 2, 3, 4, 5, 6. Now, it could have gone down that chain, could have gone to the other side chain, it doesn't really matter. You've got a side chain here, and you've got a double side chain here. Now, methyl takes higher priority over ethyl. We'll learn about this later. Please don't worry about it. It's just the shorter the side chain takes the bigger priority. But in this case here, what we're saying is that we have two methyl groups. So they're both at 2. So we're going to say this is 2 dimethyl. And we have a ethyl group at 4. So we have 4 ethyl. Now, which one goes first? Well, the one that goes first in the naming, and this isn't priority when you're counting, this is the naming. Which one goes first is the one that is lower in the alphabet. Ethyl is lower than methyl. Yes, I have di with a D, but we don't count that. We only look at this part here. So this part and this part. So looking at those parts, E is before M, so it needs to go 4 ethyl to 2 dimethylhexane. So this one here. If the substituent is repeated on the same carbon, repeat the numbers. So 2 dimethyl, not 2 dimethyl. So I've already discussed that. Generally, commas are reserved to separate numbers, dashes separate words and numbers, spaces generally shouldn't appear. So you know how I said, like here, you've got dimethylhexane. As much as it reads like dimethylhexane, it reads like 3 words. Dimethyl sort of flows, but methylhexane, that reads like 2 words. That reads like a name. It reads like, there's a space in between, but don't put the space. Not going to lose marks for putting a space, but it just looks better. And for those of you who do want to follow chemistry further, don't put the space. It shouldn't belong there. The longest carbon chain is used to derive the parent name, so always do that. And then having smaller numbers is generally preferred. That's the other thing as well. So I want everyone to have a go at this one. For those of you who are watching the recording later on, please pause the video and have a go at this. For those of you who are here at the premiere, I'm going to give you a very short amount of time. I'm going to give you 30 seconds because I don't want to be, wasting too much time. So 30 seconds and have a go right now. So you can see the time in the top right, 35:30, we are going to go through this. So work through the systems that we just worked through. All right. 3, 2, 1, let's go. So we have a chain that is 1, 2, 3, 4, 5, 6, 7, 8 long. Now, remember, we're going to count 1, 2, 3, 4, 1, 2, 3, 4. So in this case here, we're going to count from 1, 2, 3, 4, 5, 6, 7, 8. So in this case here, if you count it the other way, you get the ethyl is 4 and the methyl is 5. We're going to count the methyl first. We go 1, 2, 3, 4, 5, 6, 7, 8. So in this case here, we're going to say this is 4 methyl, this is 5 ethyl. We've got oct as our main, and ethyl comes before methyl in our naming. So we're going to say 5 ethyl, 4 methyl, octane, and that is our answer there. So what if the only ice cream flavor was vanilla? Well, that's pretty boring. Hydrocarbons are boring. So we need to spice them up. We need to incorporate some functional groups and, get those flavors that are not vanilla. So how many classes of compounds are defined by the presence of functional groups? Many, 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 and many. So these are the ones that you're sort of going to need to know. Now, they are in different colors for different reasons. Haloalkanes are like everywhere, everywhere, everywhere. You need to know that super well. The ones in red there, you also need to know super well. They come up all the time. Both of those, you need to know how to name, number, write out, identify everything. I've put haloalkanes in green because they are the most common. The blue ones there, amines and amides, are slightly different. This is on the basis that you need to know how to identify them. You need to know how to identify them when they're named. So if you're given the name of the molecule, you need to know how to identify that it's an amine or an amide. You need to know the general structure of them. But if you're given a picture of one, so you're given a picture, and the picture, is like it's an amide or an amine, and you can tell that, you don't need to know how to write out that molecule. You don't need to say, all right, this is 4-pentine, like it's like pent-14, 1 amine. You don't need to know how to draw. You don't need to know how to name that. You can be given one and you can identify it as an amine. You don't need to know how to name it using the IUPAC for amines and amides. So they're slightly different in terms of they just put less sort of push on you to do that. It's also the same with aldehydes and ketones. The only reason I've put them in here is because they're quite useful when it comes to our pathway of alcohols to carboxylic acids. Now, again, you don't need to know how to name them. So you don't need to know how to go, all right, that is pentan 2,1, or that is pentanol. So pentanol would have, an aldehyde group on the end. You don't need to know how to name those given if you were given the image again. Same thing as amides and amides. The only difference there is they're really useful when we look at alcohols to carboxylic acids, and you kind of need to know how to work with them a little bit more than amides and amides. Amides and amides become important when you get to food chem. So again, don't need to know how to name them, and even in food chem you don't need to know how to name them, but they do come up in food chem. So they kind of get more influence in food chem, and they get more of like a, hey, look at this, you need to know about this, rather than right now. You do need to know these reactions as well, but we will talk about them when we get there. So, moving on, let's start with haloalkanes. Most common is chloro. It's always going to be chloro, chloro, chloro. If they give you something else, well, it's not that bad. You're going to know how to work with it, but that's a little bit annoying because they usually only give chloro. It's the presence of a halogen group or a substituent that changes the reactivity. They're used as sort of synthetic precursors because it's really easy to add these things on to just basic hydrocarbons. And then from there, that makes it easier for that to sort of add something else on that you want. As you can see here, we just add chloro in. So we just say, hey, chloromethane. This one's a really complex one, so it says like, hexachloro ethanes because there's 6 of them. You're never going to have to add 6 in, don't worry. And then here's a benzene ring that has a chlorine added to it. So we say chlorobenzene. Now, I do want to look at this skeletal structure very quickly. Ignoring this benzene ring is a little bit different in terms of that. Ignore the benzene part. This skeletal structure shows that there is a carbon here. There's a carbon here, carbon here, carbon here, carbon here, carbon here, carbon here. Now, ignore the ring. This little section here, is there a carbon here before that chlorine? There isn't. Why is that? Because at the end, they've drawn a molecule. So when you have a skeletal structure, if you draw a molecule at the end, so you say, I'm working with molecules like this, and then I put OH at the end for an alcohol. What I'm working with here is a prop, not a bute, I'm working with a prop. If I just drawn this, that's bute. But because I put the OH here, it becomes a prop, and that is propanol, or propan-1-ol. That is just saying that there is an OH off this carbon. So you have to draw that extra line, and you have to make sure you know that that's not actually a carbon again. So then alcohols, as we just talked about, alcohols have an OH group. The most common is ethanol. Ethanol is used in lots of things. It's used as fuel. It's used in alcohol, as in like drinking alcohol. Methanol is mainly used in sort of hand washes, those the hand sanitizers we've all been, loving over the last 2 years. That is methanol. And then you have sort of propan-2-ol. So propan-2-ol here is just another version of an alcohol. Now, alcohols have OHs. The really cool thing about alcohols is you also have this thing called primary, secondary, and tertiary. What's that mean? Primary alcohols have the carbon that the alcohol is connected to only has one carbon coming off it. So what we're talking about is this carbon here only has one carbon coming off it. This carbon here, which has the alcohol on it, has two carbons coming off it. This alcohol here and this carbon has three coming off it. Now, I don't know why I put 1, 3, 2, 1, 2, 3, you know what I mean? So this is primary, this is secondary, and this is tertiary. 1, 2, 3. As you can see there, 1, 2, 3. So that carbon has 1, that carbon has 2, that carbon has 3. And so there are different things you can do with these alcohols. So please remember them. We are going to move into how we work with them in a little bit, but do remember them because it is an important rule to know. So, ketones, so these are really important. You don't need to know how to name them for VCE. However, they do end in 1. So they go 1. That's their suffix. They do have a prefix as well, but we don't worry about it because, as I said, you never need to know how to name them, and usually most of the time they're sort of by themselves. Now, a ketone is a carbonyl group. A carbonyl group is a double bonded oxygen. This is a carbonyl group, and a carbonyl group that's bonded secondarily. So it cannot be tertiary. So first of all, cannot be tertiary. Why can it not be tertiary? I want you all to take 10 seconds to think about that. Why can a ketone not be tertiary? Because it's got a double bond. Pretty simple. If I have a carbon with a double bonded oxygen, I can only maximum add 2 more bonds. I can't add a third bond for 3 carbons. That's just wrong. It's just bad chemistry. It's a sin. So what's really important about these is understanding they can only be secondary because if it's on the end, that's an aldehyde, and we'll talk about that in the next slide. So ketones are carbonyl groups found in the middle of a molecule, and they are always secondary. So they're always secondary, and they end in 1. So you do need to know that they end in 1 because you may get a question that says, pentan 1, and then you need to identify that's just a ketone. Now, aldehydes, on the other hand, they're the same thing, but they're on the end. So they're always primary. So instead of having a primary alcohol and a secondary alcohol, and instead of having, a primary carbonyl and a secondary carbonyl, we have an aldehyde and a ketone. They've got their own names. Aldehydes are far more useful. We use aldehydes in things like formaldehyde, if anyone has heard of that. Formaldehyde is what we use to preserve dead tissue. So we preserve bodies. We preserve, like when people have their dead animals in a tank that uses formaldehyde. You will have heard of formaldehyde before, I'm sure, at some point. It's used in lots of those crime TV shows and things like that. So formaldehyde is really the most common aldehyde that's used. Aldehydes are really, really useful. And we'll discuss why in a little bit, but they are primary. They end in al, so you might have pentanal, or in this case here, you've got ethanal. So in this case here, this molecule is ethanal. Usually you don't need to number these ones because it's always on the end and they're usually by themselves, so you don't need to bother numbering them. But if in some complex reason you've got something else there, you're going to have to do some numbering, but don't worry, it usually doesn't need numbering. But as I said, you don't need to know how to name them for VCE, but just a cool sort of fact. Now, carboxylic acids. Now, carboxylic acids use the suffix oic acid. Now, these are the most common ones that come up. These are really, really, really important. So please understand these out of today. So a carboxylic acid has the suffix oic acid. It does not have a prefix. Now, you do need to know how to name these as well. They do not have a prefix because they are the highest priority. These are the highest priority. These will always be number 1. You will always count from the end with the carboxylic acid. Now, why do I say count from the end with the carboxylic acid? Because carboxylic acids are always at the end. They're never, ever anywhere else. They're always at the end. They're always 1. So you are never going to write propan 1 oic acid. You are never going to put that 1 in there. Why is that? Because it's always priority 1. We always know where it is. It's always going to be at the end. As you can see here, This is an really good example because it's got a methyl group. We've given the methyl a number, but the oic acid we haven't because the oic acid is always on the end. Again, here, propanoic acid, same thing, it's always on the end. It also has a space between the oic and the acid, really important. I know how I said before, there's no spaces. This is one of those ones where there is a space because it's a separate word. You're adding acid as a separate word, so it's oic acid. Really important you put a space there. So these are always priority number 1. Then we have esters. Now we will discuss how esters form, so please don't worry, we are going to talk about that. But esters sort of form from alcohols plus carboxylic acids. What I want you to get out of this slide is how to name them. So esters have this cool C-double-O bond. If you are asked to write a semi-structural formula, so this one here, example, you're asked to write a semi-structural formula, you are going to write CH3, C-double-O, CH2, CH2, CH3. Sorry, I ran out of room. But that is how you would write the semi-structural formula for that molecule. You don't need to go, CO double bond O, a double bond to an O. You don't need to put the double bond in there. You're just going to write C-double-O. That is how you semi-structurally write an ester. Now, esters is really cool. They come up all the time. Huge in food chem as part of our proteins and our also huge in our fuels because they're really, really important in our biofuels. And you've already discussed that, but you'll discuss it further in food chem because it comes up again. What's really important is they have 2 words. This is split up again into 2 words, and it's il, oate. Now, also kind of cool, they sort of, with the alcohol, unless there is any like double bonding or triple bonding, so unless you've got like an alcohol that was like this, and then, you had your OH group here, unless you had like this, and this will never happen. I'm just saying it could happen, but it's never happened, and I doubt it will ever happen. You are always going to have alcohols that are single bonded. You're always going to have ane alcohols. So for the sake of VCE, when your alcohol, for this case, we're going to use this one. So we'll say this is propan-1-ol. We're happy with that. It's propan-1-ol. So propan-1-ol, as part of your alcohol part of your carboxylic acid, is going to form propyl. You're not going to put the ane in there. You're going to get rid of it. You're just going to say propyl. So this is propyl. Then your carboxylic acid. So let's just say, I'm going to rub this one out and draw it here. So then let's say we have a carboxylic acid, and let's just say it is this carboxylic acid. This is ethanoic acid. We're going to write ethanoate. So you keep the an or the ene or whatever it is, you keep that for the carboxylic acid part. A little bit frustrating, but it's just the way things work. When you do have something weird in your alcohol, you then go and change this up. But that is beyond the scope of VCE, and you do not need to worry about that. As you can see here, this molecule here, if I name this one, it's a little bit different. So when I'm naming it, I need to figure out what part was the carboxylic acid and what part was the alcohol. Well, if I say, and I'm going to say to you, it splits here. This is where it splits. Which part here has to be the alcohol and which part here has to be the carboxylic acid? It's more which part has to be the carboxylic acid. Which part has to be the carboxylic acid? Hope you thought. 3, 2, 1. It has to be this side. Why is that? Because it's got the double bond row. So this side is 1, 2. So my carboxylic acid was ethanoic acid. So I'm going to have ethanoate. What about my acid? Well, my acid was 1, 2, 3. No, sorry, my alcohol. My alcohol was 1, 2, 3. So this was my alcohol, and it was exactly like what we wrote before. It's going to be propyl ethanoate. Now, 2 words, so there is a break in there. There is a gap. But that is propyl ethanoate. Then last 2, amines and amides. Again, you don't need to know how to name these. They very rarely, they do, like this will come up and you'll need to know how to sort of identify it, and they'll have this come up and you need to know how to identify it, but you never need to know how to write it fully down. They end with the suffix amine, or they start with the prefix amino. This will come in handy because you can look at things like amino acids. Ethanamine is another example there, methanamine, etc. Amines can be secondary, tertiary, primary, secondary, or tertiary. What's really cool about this is it comes off the end. So if I write out this molecule here, H, 1, 2, 3. this is primary. Now, if I draw out this molecule here, can I get rid of the, oh no, I can't. If I draw out this molecule here, I don't need to draw out the hydrogens, I'm just going to, just for the sake of it. This here is secondary. Now, if I draw out, I'm going to come over here. If I draw out this, and then these all have hydrogens coming off it. That last one was terrible. That is tertiary. So, you've got primary, secondary, tertiary amines. They do come up, they're a little bit different. And they base themselves off how many carbons come off the nitrogen. Now, amides, these are, again, a bond. So you've got carbons on either end of this, and you've got a chain coming off it. Now, amides are important more for biology than chemistry, but we do talk about them very briefly because there is a peptide bond. Now, they end with amide instead of amine, so their suffix is amide. Don't worry about a prefix, it doesn't come up. These are the links that link together amino acid residues, and you will talk about these far more in food chem for that reason. So, pushing through, here's a really cool summary slide. Now, this is the sort of summary slide that I don't really want you to go and take a screenshot of this and then paste it in your book. What I would want with you, with all of you for this summary slide, is to go ahead and actually do make your own version of this. This is really super useful. It's something that would look really good in not only a workbook or a summary book. It's something that allows you to sort of come back and go, all right, what are some just really good examples? How do I name, what do the groups look like, etc. So it's a really good summary slide for that. It's all the functional groups you need to know. It's got all the names, everything like that. So it's a really good way of going about it. So again, they want you to have your own turn. However, I think what we'll do is, for those of you who are at home, please feel free to have a go at this. I think what's best for those of you at the live stream or the premiere, have a go at this one here. I'll go through these ones, and I will go through this one, but I'm going to give you 30 seconds. I want you to go through this one here only, because in 30 seconds you're only going to get one done, even if you do get one done. Have a go at this one. Your time starts now, so at 12:55, we're going to go through it, as you can see up here. Amazing. All right, that's your time up. Let's go through these. So I'm going to start at the start, then I'm going to go to the other ones. So starting with this one here, let's go to our longest chain. We've got 1, 2, 3, 4, and then we've got a single chain here. So we've got this is a ester. So we've got an il O8. So let's figure out which one is the il. We break it here. This is the il. So we've got butyl, and then we have meth, because there's only one, so meth and no weight. Butyl, methyl noate, it's an ester. All right, next one here. So what's going on in this one here? So longest chain, 1, 2, 3, 4, 5, 6, 7. Going to count from down here because that's the closest to that. So 1, 2, 3. So 7. 7 is going to be hept. They're all single bonds, so it's going to be ane, and then this is at the third carbon, so it's going to be heptan 3 ol. Oh, whoops, I need to put another dash in there. My bad. Heptan 3 ol. Heptan 3 ol. Now, lastly, this is what I got you guys to do. So 1, 2, 3. So there is a chlorine molecule here and a bromine molecule here. This is closer to the end, so we're going to prioritize from here. They're both the same priority, but because the chlorine is at an end, we may as well count from there. So 1, 2, and then this is the third one. So this is going to be 1 chloro, 2 bromo, but B is before C. So it's going to be 2 bromo, 1 chloro, and then this is going to be propane. 2 bromo, 1 chloro, propane. Very good. So, very briefly before we get into reactions, just want to quickly talk about, also just having a look through, I don't think I put a priority slide in. So I actually, just very quickly before we jump into this, I want to talk about priorities. So I'm just going to go priorities. Now, what's really important about your priorities is just remember this basic priority list. One is carboxylic acids. 2 is alcohols. 3 is side chains. 4 is haloalkanes. Now notice I haven't included any of the other ones because you don't really need to name them. They don't come up. And as I said, some of them you don't even need to know how to name. So I haven't put them in there. This is the priority. And this is not the priority of how you this isn't the priority in sort of how you name it, like if you've got multiple prefixes and multiple suffixes and all that sort of stuff. This is the priority in where you count from. So which carbon am I going to count from? Which bond am I going to count from? This is that. So this is the counting priority. That is what this is important for. Now, what that means is that if you have both a carboxylic acid and an alcohol, so say you've got molecules like this, and then you got carbon, you got OH, and then, that's what I'm going to draw. That's all I'm going to draw. That's your molecule there. This molecule here, this is going to go as the suffix. This is going to be a prefix. So you need to know a prefix and a suffix for both of these. Particularly for your alcohol. And so the suffix, which is most commonly used because usually you don't have a molecule like that, is ol. But if it's a prefix, it's hydroxy. So hydroxy is your prefix. In that case, there you're going to count from this end, and then your prefix would be your hydroxy. Now, that's just what's really important here. You just need to know that, and then this is the name. This is the priorities of counting, so where you count from. So if you've got both an alcohol and a halogen, you're going to name from the end that's closest to the alcohol, not the halogen. So that's sort of that priority group. So moving back, the last thing with sort of organic chem before we get into reactions of organic chem, this is just like the basics, is isomers. So I'm just going to go very briefly over these just because a lot of it is sort of revision, but then the new topics, which are geometric and sort of optical, which are the new things for year 12 isomers, can get quite confusing, and I don't expect you to understand it after today. I just want to sort of give a brief little understanding of what it is. So isomers in year 11 were this, and this was not a thing. Now in year 12, this is now a thing. So you do need to know about stereo, and they're the ones we're going to go through today. Now structural isomers are what you did in year 11. I'm not going to read through that. It doesn't even go over it. I must have gotten rid of it because I've literally thought like it's year 11 revision. I'm not going to spend too much time. Structural, just remember, structural is literally like, you've got butane, and then you go and you have butane, looks like this. And then you essentially go, all right, actually, I'm going to make this. These have the same molecular formula. So C4H10, C4H10. They both have the same molecular formula, but they're just drawn differently. Stereoisomers differ in terms of there's no big structural change. You have just like subtle differences in how they are displayed in three-dimensional space. And there are two forms of that. There are optical and geometric. Optical are the ones that are really confusing. Geometric are pretty straightforward. And geometric, again, really big in food chem. So you go through geometric a heap more in food chem as well. So we'll start off with geometric. Geometric essentially means if you've got a double bond and you've got a functional group on either side of the double bond. Now, it has to be on either side. It cannot be like, you can't draw this. These are two functional groups on the same side. This is not going to have geometric isomers. They have to be on different sides. As you can see here, they're on different sides in both cases. Now, what's really important about this is it doesn't just have to be a functional group. It just cannot be a hydrogen. So it could look like this. So you could have like molecules like this. Then you have a hydrogen down here. And then you have a hydrogen up here, and you have a chlorine down here. Now, in this case here, I probably should have drawn this a little bit better. As you can see here, this is one functional group, this is another. I know this isn't necessarily a functional group, but we treat it like a functional group. It's different. You could have done the exact same thing down here. You could have said, carbon with 1, 2, 3, exactly the same thing. They are referred to as functional groups just because they're not hydrogens. Like if they're hydrogens, it doesn't work, but they're not hydrogens, so it does. Now, what the difference between these two are is that this double bond here doesn't allow this to rotate around like this. So if I have a single bond, think of it like two fingers. I have a finger, so I've got, that's a good way of doing this. I have this. Think about it, this double bond can sort of rotate, and these are carbons, my hands are carbons. See how my carbon can just rotate really easily? Now if I'm like this, and I want to rotate my carbons, they cannot rotate, because when I go to rotate them, the double bond gets in the way. The double bond doesn't allow me to rotate. There's no rotation. So that's what happens here. So this is what we're talking about. These are not the same molecule because this cannot rotate around. This is not possible. It's not possible for that to occur. If this was a single bond, it would be. Because it's not a single bond, it cannot. So these have different names. This here is trans, opposite sides. This here is cis, same. I remember it as cis, same. Cis means same, trans means opposite. But the best way of remembering it is cis, same, cis, same, cis, same. It just reads, it just flows off the tongue. So I remember it as cis, same. These are on the same top or bottom. These are on the same. So these are both at the top. This one here, they're in different. One's at the top, one's at the bottom. So trans, different, cis, same. But cis, same is the best to do it. Is the best way to remember it. So they cannot rotate around the double bond. Therefore, in three-dimensional space, they are different. Optical isomers, these are really confusing. So we're just going to go very briefly, just give one very brief example of it, and then that'll be it. Because this can just get really, really confusing, and I don't want to spend too much time on it. Optical isomers are the same molecule with different places for each of their functional groups. Now, what I mean by this is, this carbon is a chiral carbon, and this chiral carbon is called a chiral carbon because it has 4 distinct different things coming off it. It has a CH3, it has an OH, it has a H, and it has a COOH. Now, if I drew a molecule like this, double bonded to a C, and yes, I put a chlorine there, and then I have 1, 2, 1, 2, 3. You'd say to me, well, everything's different. This was a CH3, this is a CH2, and this is a chlorine. So I've got 3 different things coming off it. Isn't this chiral? Well, no, because there's 2 bonds here. So essentially what you think of it is this carbon, I'll draw it up here. This carbon is bonded to 1, a CH3, 2, a Cl, and then 3 and 4 are both bonded to a CH2. So therefore, these are the same, therefore this is not chiral. You need to have 4 different things. So you could have a carbon that's like this. That's a hydrogen, and then this is a chlorine. This is a chiral carbon. Why? Because 1, it's bonded to a CH3. 2, it's bonded to a hydrogen. 3, it's bonded to a chlorine. And 4, it's bonded to a CH2CH3 or a C2H5. So they are 4 different things. This is a chiral carbon. So in this case here, these are chiral carbons. And notice how these chiral carbons, just getting rid of all this scribble, notice how these chiral carbons here are different. Because if I went to put these on top of each other, they would look different. The CH3 would be here, the H would be here. These are different. Now, please ignore the little triangle thing. They're just saying like one of them is up towards you and one is down into the page. Don't worry about that. As you can see here, what we refer to that as is the inability to superimpose. Now, the best example for this is your hands. Take one hand, put the other hand on top of it. I can't match my hands. It doesn't work. The only way I can do it is put it backwards, and that's not the same. If I try and put my hands down on top of each other, they're different. My thumb is here and my thumb is here. They're non-superimposable. When something is superimposable, when you put them on top of each other, they are identical. These are mirror images, and therefore they are not superimposable. Therefore, they are different. Now, this is a really key concept. It's actually been very clinically and like in real life been a proper topic. There was a medication, I forget the name of it off the top of my head, I always forget it. It was through like the 60s, 70s, 80s, I believe. One of those eras. It was a morning sickness medication, and they didn't realize that there was a chiral carbon in there. So if you had one version of that chiral carbon, it treated morning sickness. If you had the other version of chiral carbon, it did treat morning sickness, but it also caused damage to the unborn child. And therefore, a lot of the children that were born on this medication ended up coming out with birth defects because those mothers were unlucky enough to buy this medication that cured morning sickness and take this medication, but they were taking the medication that just unluckily had the chiral version that was bad. And the company that was producing it didn't realize at the time, and then they did come to that realization, obviously got sued, that drug isn't used anymore, lost a lot of money, but essentially that's a real life implication of this, that there was two versions of it because of a chiral carbon. One of them was fine and the other one was not. So it's important to understand that. So moving forward, so we're going to move into our reactions. So we've got 5 different reactions. We're just going to move straight into them. So we'll start off. This is the most basic and common one. This is a substitution reaction. This essentially involves taking one thing out and putting something in. It's like soccer or a lot of football. It just depends sort of how you refer to it. I always tend to refer to it as soccer just because AFL football, but I know it's really football. It's more of a football than our football. But we're going to say soccer just for the sake of it, to simplify things up. In soccer, you have, well, it used to be 3, it's now 5 substitutions. Those 5 substitutions essentially are that you can take a player off and put a player on. That is the same thing as a substitution reaction in chemistry. You can take a hydrogen or a chlorine or an alcohol off, whatever the off molecule is. You can take it off and you can put something on. You can put a hydrogen, you can put an alcohol, you can put a halogen, you can put whatever you want there. But you've taken something off, you put something on. That is a substitution reaction. So as you can see there, that goes on, something comes off. Well, that was really bad, I got rid of it. The green comes on, the brown comes off. Green on, brown off. So, as you can see here, this is a great way of simplifying it. You look at those memes. So, a really good other way of looking at it is looking at how it works in terms of organic chem. So, for chlorine, this should also have heat. So, for chlorine, which is the most common example, and it's why we are going to use chlorine as our example here. If you have chlorine gas and you have a, let's just say ethane or an alkane, if you put that in the presence of heat, so you heat it up and you put it in the presence of UV light, what happens is the hydrogen will come off and the chlorine will go on. And you end up with obviously a byproduct of HCl, but as you can see here, you've formed a haloalkane. Now, importantly, you cannot control, there are ways that are way too technical and you don't need to worry about it. For the sake of chemistry, 3-4, you cannot control where that chlorine goes. That chlorine will go anywhere it feels. So, really important. UV or heat is required, essentially it's required to break the halogen molecule. So that's what's really important. It acts as a catalyst. You must write UV heat. And I don't think it's or, I say and. It's really interesting. Some teachers and some, because I've been tutoring for a long time, so I've seen how different teachers teach students because then they come to me with questions. Some teachers have said or, some teachers say and. I was taught to always put both. So I put both. I would feel more comfortable, and I tell my students all the time, put both on your arrow. If your teacher's told you to do one, you're welcome to do it, but I feel more safe doing both because it also shows that you know both as well. So I think putting both is important. So moving through. Substitution of haloalkanes. So haloalkanes can also I think I was going to go under substitution reactions. Haloalkanes are much more reactive than alkanes. So I think I was going to say can also undergo. I do apologize. I think that was my poor typing. When alkanes, alkanes because the polar bond undergoes a bunch of different types of substitutions. One such example is the formation of an alcohol by substituting in a hydroxyl group, which can undergo further substitution to form an amine. So as you can see here, what happens is you've got your chlorine comes off, and your alcohol goes on. Now this, as we said, haloalkanes are far more reactive. You don't need anything on this arrow because it's far more reactive. It happens in a far more reactive way. There are things you can put on that arrow, but as I'm saying, it's far more reactive. It's more likely to happen. You don't need to have the heat and the UV to force it. As you can see here, when you want to add in, that's meant to be this one down here, sorry, I don't know why, or this one down here. If you want to add in an NH3, it is a little bit different. You do need some you do need some catalysts, and as you can see there, it's Al2O3 and 400 degrees Celsius. Now, addition reactions, these are, again, a little bit different. Now, these, you are either a substitution or an addition. You're not both. Really, really important. They are the two that are distinctly different. Addition is when you don't take something out, you just break a bond and put something in. So it's when you're sort of saturating a molecule that's unsaturated. So as you can see here, we have an unsaturated molecule. We add the bromine or the bromide gas, and it goes in, or the bromide liquid, depends on what form it's in, and it goes in and forms, well, it'll be 1,2 dibromoethane. Now, what's really important here is you can't put two bromos on one. You can't say, oh, there's a Bi here and a Bi here, because when that bond breaks, there is a spot here and a spot here. So the bromo has to go here and the bromo has to go here. Really, really important. Comparing alkanes, alkenes are fairly, compared to alkanes are fairly reactive. So unlike substitution reactions, there's no inorganic product formed as well. So there's no, byproduct formed. There's three main types. These very rarely come up, but it's just kind of good to know. There's hydrogenation or hydrogenation. This is where we just add hydrogens in. So essentially just saying we're adding hydrogens in, we're saturating with hydrogens. There's halogenation. It's where we saturate with halogens. You can also saturate with like a HCl and put both a hydrogen and a Cl. It's still halogenation because you've made a halogen. Then there's hydration, which makes sense. You add water. Now, these are really important catalysts to remember. H3PO4 at 300 degrees. This is hydration because you're adding water and you end up with an alcohol group. So one hydrogen goes by itself, the other one ends as an alcohol group. Now, beyond that, that's about it. I would also like to talk about this just very briefly. This is what we call a bromide test. This comes up pretty frequently. This, as a liquid, is brown. This, as a liquid, is clear. This, as a liquid, is also clear. So, if you have an unknown hydrocarbon, you don't know what it is. You have no idea. You've just got a solution, and you've got a solution of bromide liquid or bromine liquid. You've got a brown solution. What you do is you add this in. Now, when you add it in, it's still going to be brown. Like, sure, you're adding a clear into it, but it's still going to be brown because you've got bromines in there. So it's going to be brown. When you add this in, if it all goes clear, if it adds in, dilutes, and then all of a sudden it goes clear, like after a couple of seconds it goes clear, everything disappears. What that tells you is that all of this has been used up into this. So it tells you that you had an unsaturated molecule. You had an alkene or an alkyne. Now, if the solution stays brown, it means you already had a saturated molecule. Your hydrocarbon you added in was already saturated. So, therefore, your bromine or your bromide, your liquid was unable to react. It wasn't able to disappear, so you still got that molecule in there. It's still brown. Therefore, you had a saturated molecule already. That's a bromide test. So that does come up. Important to know. Yeah. Pushing through because we are running out of time for this side of the topic because we are, we're already like an hour and 8 minutes in, which is pretty good. So I think if we get this done in an hour and 15, we can move into the second part and spend about 40, 45 minutes on it, which is pretty good. Oxidation reactions of alcohols. So alcohols essentially can go through primary and secondary alcohols or alkanols, same thing, can be oxidized by really strong oxidants. So as you can see here, you need to remember one of these. So H plus with Cr2, so it's dichromate, Cr2O7 negative, or a word I can never say right, penanganate, I can never say it right, but it's H plus with MnO4 negative. Now, these are really, really nasty molecules. They're really strong oxidants. You add them in with alcohol and you're going to get either a ketone or a carboxylic acid. There will be aldehydes in there, but there won't be many. I'll explain why in a second. You essentially get this pathway here. You get primary alcohols going through a two-step pathway. You get an aldehyde in the middle. However, these aldehydes are highly reactive, and 99% of them will go into this. 99% of them are going to continue on the pathway and go to carboxylic acid. That is why I said you're pretty much just going to have carboxylic acids and ketones. You're not going to have any aldehydes because aldehydes are so reactive they just move forward. Ketones form from secondary. So if you have, this is what you form, this can no longer form a carboxylic acid because you can't add an OH group here. You've already got 4 bonds. This isn't possible. So that's why secondary alkanols cannot form carboxylic acids. They're not as useful. They just form ketones. And ketones are really not that useful. Tertiary cannot even form a double bonded oxygen because tertiary, if you think about it, and there's a carbon here, and then you've got your OH. If you want to form a double bond there, you end up with 5 bonds. So again, not useful. So that is why primary alcohols are the most useful and the ones that we're going to utilize the most. And as we said, secondary alkanols form ketones, really not that useful. Now, tertiary alcohols don't undergo oxidation. Cool. Now, this is oxidation. You've already been through redox, so it should be pretty sort of straightforward to understand. Now, this is what the pathway looks like. As you can see, you've got the same catalyst for both. The same catalyst for both is really, really important. Please don't write dichromate on one and then penanganate on the other. You need to stick with one of them. And it doesn't matter which one you use, just pick one and stick with it. And that's sort of how you go about it. And then here's secondary. As you can see, it's just one step. You can't go any further. Also, sort of kind of relevant because you may use it in sort of an experiment. Dichromate is generally orange, whereas penanganate is like a purpley navy color. So it's kind of useful to see. You can kind of utilize those and utilize that information in questions. It's quite useful. So do sort of try and remember that. And that's sort of about it. So it's kind of useful to know that. I'd say that's probably about it from that side of things. And then we have esterification. So esterification is where we form our ill OH, and we've already talked about this very briefly. But as you can see here, you have a carboxylic acid with a primary alcohol. Really important, you have to put it with a primary alcohol, and it yields an ester. So this is a condensation reaction, which releases H2O. You need to heat the reaction mixture with the presence of concentrated H2SO4. Now, really important, you either write concentrated or conc with a full stop, I mean concentrated, H2SO4, or you put H2SO4 liquid. Both of these are acceptable, but nonetheless, you just need to do one or the other. So we've got, as you can see here, you've got ethanol and you've got propanoic acid. You put them together with H2SO4 and you end up with this molecule here. Now, what's really important, and this is what we didn't discuss earlier, is what is lost. This is lost and this is lost. When these come out, what do you think they form? You've got 2 H's and an oxygen. What does that sound like? It sounds like H2O. So you have H2O as a side product. For those of you who do biology, you will have heard of this as a condensation reaction. And that is what this is. This is also a condensation reaction. You can call it either condensation or esterification reaction. Either of them work. I don't mind. I'm happy for you to go with either of those. So they're the 2 things that you need to know. So here's a really good question. So what is the systematic name of the product of this that this reaction forms? Again, those of you at home, feel free to pause and take your time. Those of you here, I'm only going to give you like 20 seconds. So you're going to get 20 seconds from here. So go for it now. All right. So from here, what have we got? We've got a chain that can start either here or here. Doesn't really matter. You got 1, 2, 3, 4, and then an alcohol. So I'm going to call this, this is going to be bute and 1-ol, but it's also going to have on the other end, so I probably shouldn't use a capital there. I should use a lowercase. On this end, it's going to have a methyl group, and that's going to be at the 1, 2, 3. So it's going to be 3 methyl butanol. It shouldn't have a space, but the way I've written it Sorry. All right. Then from here, we are going to go, all right, if I put this in and I go forward, what am I going to end up with? Well, I'm going to end up with an oic acid. You may end up with an aldehyde, but as you can see here, it's only giving you oic acids. So we end up with an oic acid. This is still going to be butanoic acid. So it can't be A or B. It needs to be butanoic acid. And this is going to be at the first spot. So this is going to be an O. This is going to be an OH. That's going to be 1. This will be 1, 2, 3 again. So it's going to be this one here. 3-methylbutanoic acid. Answer here is D. So this is what we went through. We went through loads and loads and loads of things. This is a really good summary slide of everything we went to, but nonetheless, pushing forward. So topic 2, analytical chem. As you can see, we've been running for about an hour and 15 minutes, which is pretty good. So we have about 40-45 minutes to go through analytical chem. As I said earlier, there's loads of slides, but we're not going to go through everything in super detail. There's lots of slides that I'm just going to push through and not going to spend a whole heap of time on. So please don't stress about those. And this is essentially just going to give you a very brief overview. I don't expect you to come out today understanding everything about this. So what is analytical chem? What analytical techniques can we use? How can we use them to analyze? That's what we're going to come out of today. So essentially, what we do in analytical chem is how do we figure out what the compound we have in the first place? So when you have like a solution, you don't know what it is unless it's labeled. So how do we figure it out? This is what we do. Analytical chem uses fancy instruments to separate, identify, and quantify molecules. In Unit 4, we are only concerned with organic compounds. So just like organic compounds, chemistry has billions or bajillion really important real-world implications. Suppose you're at a crime scene, you find suspicious powder. How do you know if it's dangerous or not? Perhaps you get put over the side of the road, you do a random breath test. How do the cops know you've got ethanol in your system? This is essentially the same thing. These all use analytical techniques. So we separate using chromatography. We've discussed these in year 11 already. You need to sort of refresh yourself on these. There are slides on it. I'm going to skip over the slides on it, but I've left the slides in there on purpose so that all of you who want to go over it can click into the slides, scroll down and find those slides and go through it if you would like. There is identify. There is spectroscopy, which is the main proportion of this topic, and you're going to spend most of the time on that. Then there is quantify, and this is like acid, base, and redox. We've been through these before. We went through these in sort of topic in like Unit 3. Acid, base is sort of like titrations. We sort of recovered a little bit. I don't think I've put any slides on it today. I think I've left it out, but it's another thing from year 11 you sort of need to know how to do. So really important you know your titrations. Again, this is all the stuff from the study design. And then these are the chromatography slides. I'm not going to spend too much time on them. I want you guys to sort of, if you feel like it and you feel like you need it, please go over these slides. They have all the information you need, but that is all year 11 stuff that you should be able to revise yourself. So let's jump in to this. Spectroscopy. How do we identify? So we use chromatography, we've separated all our mixtures, and now we're going to figure out what are our mixtures. What have we got? So we use spectroscopic techniques. Now, this is just referred to as spectroscopy. Now, they use different forms of EM radiation or electromagnetic radiation, and they find what's going on. So if we have an unknown organic molecule, what might we be useful to identify it? Well, we want to identify the molar mass, we use mass spec. We want to identify the functional group, we use IR spec. And we want to identify how it all connects together. How are the molar mass, where is, the functional group in it? Where are just the carbons? How many carbons? Are there other things? That is all the connectiveness is NMR. NMR is really, really confusing. Mass spec is, I'm going to be honest, it's really simple to get your head around it. Most of you will probably come out of today understanding it. If you don't, that's okay, but you will understand mass spec pretty quick. IR spec, also sort of simple. It's a little bit more difficult, so it might take you a little bit longer to switch onto it, but it is also something that I expect, 30-40% of you to come out of today and say, hey, I understand IR spec. NMR, if you come out of today understanding NMR with the very little information I'm going to provide you, because we're not going to go over it in super detail, then very, very impressive, because NMR is really confusing. And it takes a little bit. It'll take you 1 or 2 or 3 times of going through it to really get your head around how it works. And we're not going to go through it in super detail today. Now, what's really important about these 3 as well, there are a couple of slides in here on sort of how these things sort of work. what's really important is just have one sentence on how they work. They are really complicated pieces of machinery. There are multiple things that happen, and it is really, really, really confusing. So please just take, a good 30-second, a good couple of minutes one day when you're going through it to write out a singular sentence of how it works. So then in your head, you have that singular sentence, because understanding how they work and their machinery and all that is useful. It does make it a little bit easier, but it's just a bit over the top, and it's far too hard for all of you to remember. So moving forward, let's look at mass spec. So this is what a mass spec looks like. This is what you're going to be provided with. It looks something like this. So mass spectroscopy is a technique that provides information on the structure and molecular mass of the compound. The mass spec looks like this. So this is what mass spec looks like. We're going to go through what all of these things are and sort of how it sort of briefly works. So mass spec occurs in two sort of forms. Now, it occurs in an ionization stage and a fragmentation stage. So what does that mean? Ionization is when you get a molecule, and so you vaporize this molecule, so the molecule is in like a gaseous form. The molecule is moving through a machinery, so there might be a pipe or something, and what you do is you blast it with electrons. So you've got like an electron gun, and you blast it with electrons. You hit it really hard with electrons. When you hit it really hard with electrons, you're going to make the molecule unstable, because what you've done is you've knocked an electron off, and now it's got a positive charge. It's going to become unstable. Most, not all, but most will break. Most of them will break somewhere. There will be a break. Why is there a break? Because when it breaks, half of it can stabilize. So as you can see here, this has a positive charge. This has sort of stabilized. Same thing here. This is stabilized, and we've got a positive charge on the other end there. So essentially, the dot refers to the one that's stabilized. The plus refers to the one that hasn't stabilized, and it's still unstable, but it's more stable because it's smaller. Now, importantly, I've never seen an exam ask you to write all this stuff out. This is just a good way to get your head around what's going on. Fragmentation causes a cation and a free radical. Cations accelerate through the machine, and they hit a detector. Free radicals are eliminated in the chamber. So free radicals are not detected. The positive aspect is detected. So what's really important is they're not all going to break in the same place. You can have breaks everywhere in different places. There's usually only going to be one break, usually, but it's going to break in different spots. So you're going to get lots of different cations forming. When those cations hit, they hit the detector, and the detector can determine how big they are in molar mass. So mz refers to our molar mass. As you can see here, there's a couple of things that we should look at. The largest peak here is the peak that has the relative intensity of 100%. What that means is it's the most common. It's the one that's hit the most, so it's the most common. The highest molecular weight peak often refers to the parent molecular ion peak. What does that mean? It means we're like this. This has not broken. And for some reason it didn't break, we didn't get any free radicals, and essentially it went all the way through and got detected as a whole molecule still. And so therefore that molecule stayed complete, and we refer to that as it's the molecule's molar mass. It's the total molar mass. So tiny peaks are usually, plus or minus 1, about, around a peak. So if you have lots of little tiny peaks around a peak, what that says to us is that there are some isotopes. So we talked about isotopes in year 11, just talking about them again, but carbon's usually 12, there are some carbon 13s. Chlorine's usually 35, but there are some chlorine 37, sorry. Bromine is usually 79, but there are some 81s. So it's important to sort of understand that. So in this case here, we have propanol. So propanol looks something like this. So these are all hydrogens. So what's the molar mass of this? Like, without looking at the mass spec, let's figure out what the molar mass of this is. So the molar mass of this is 12, 12, 12, so it's 36, plus 16 is 52. 52 plus 1, 2, 3, 4, 5, 6 is 58. Now, looking at this, what is the base peak? Well, the base peak is here. It's at 58. So funny enough, this molecule here for some reason just didn't break that often. It actually was able to sustain its main mass. And then where is the highest peak? Well, the highest peak is actually 59, but it's such a small peak that you'd argue this is an isotopic peak. It's so small you'd argue it's an isotopic peak. So this is actually the biggest. So we're going to refer to this one as our, parent molecular ion. So 58 is our parent molecular ion, which matches up with the molar mass we determined by knowing what it was. So when you don't know what this is, you use this and go, all right, well, you wouldn't be given that. You use this and go, all right, mass spec, which one's the biggest? This one here, 58. Cool, I'm happy with 58. And that's what you go with. So that's how that works there. So isotopes to know is carbon-12, carbon-13, chlorine, and bromide, the ones I've already talked about. As you can see at our molecular peak here, there are two that are really distinctly big. So you would call this one the molecular peak. However, this one would also realistically be a molecular peak because these are about a 1-to-1 ratio. Yes, these ones are far less common, 99-to-1. This one's 3-to-1, but this one's a 1-to-1. So there's as much bromine 79 as there is bromine 81. So that's why they're sort of equally split. All right. As you can see, ethyl chloride, same thing here. So that is mass spec. So mass spec's really useful in terms of that. You can also determine what other little aspects are there. You could sort of like go, all right, this peak here, what is there? So actually, we'll go back to this one, so it might be useful. We've already drawn out the molecule. What is this peak here? Well, this peak here is 29. Well, if I went carbon-12, double bond to an O, double bond to a H, and let's just say this was knocked off here, it was broken here. Well, this would be positive. This molecule would be positive. Should have, So this is a positive. This here has a mass of 12 plus 16 plus 1. 12 plus 16 is 28 plus 1. This is 29. So this makes sense. This makes sense that this here is one of our bigger peaks because it makes sense that it's just broken here. You can figure out what your bigger peaks are. So you can actually go through and do that. So here are some other examples. That's mass spec. So as I said, I'm not going to spend too much time on mass spec because it's really one of the more simple ones. And I actually think most of you coming out of this now should really understand how mass spec works. Mass spec is pretty sort of straightforward stuff. It's really just useful for the molar mass. Yes, you will be asked about the largest peak. They do ask about large peak, as this is a good example where the parent molecular ion isn't the largest peak, which is more commonly what happens. It more commonly breaks. But in these other two examples here, it just happens to be that the parent molecular ion peak is the same as the base peak or the largest peak. So that's essentially that. Mass spec, done, tick. You should be all over that. The one thing, actually no, we'll move forward from that. We'll leave that there. So moving on, infrared spectroscopy. In infrared spectroscopy, we use radiation from the IR range, so it's infrared radiation that we're using of the electromagnetic spectrum. So IR spec is most useful for determining what functional group an unknown molecule has. So in IR radiation that we sort of hit the molecule with, it changes the states of the covalent bonds in the molecule, and it sort of makes it sort of shake around and look a little bit different. So don't worry too much what that means, but it just changes the energy state, and we can detect that change in the energy state. So as I said, it's a really complicated piece of machinery. It looks like it here. I don't want you to worry about that. This is a slide that's here for bonus information. If you want to read through this slide, go for it. But this is just bonus info. You do not need to know this stuff. The things I want you to get out of this is that this sentence here is pretty much all I want you to know. Infrared radiation changes the vibrational energy states of covalent bonds, which can be detected by the IR spectroscopy. That is all you need to write. If you are ever asked to write about how it works, it'll only ever be a 1-mark question, and that is all you're ever going to give. IR radiation changes the vibrational energy states of covalent bonds that can be detected by IR spectroscopy. Full stop. That is all you're ever going to write, and it's all you ever need to know. So that's really important. So IR spectroscopy also comes up in your data booklet, which is why I have this here. I had this here the whole time and haven't had to use it, but we are going to use it now. So IR spectroscopy comes up. Where does it come up? Here. So it's on page 11, figure 14. This table here is really important. Now this table here shows where you are going to find on an infrared spectrum at what wave number, so this is what our axis has, where we're going to find peaks. Now, there are some peaks that are really distinct and you're going to be able to pick them out. We'll discuss those in a bit, but this is a really useful thing that you need to know where it is. As you can see, the further up you go, you get these like more sort of stronger bonds. So, one other thing I'd probably like to ask very quickly as well, and I want you all to have a think about this. Those at home, feel free to pause and have a think. Why do these three, not these two, these three, 1, 2, and 3, why do these three specifically, I know we have our CH, but I don't want you to worry about that too much. Why do these three specifically have such a higher wavelength? Now, I'm just going to give you a clue. Higher wavelength means, you know, there's more strength involved. Why do these three? So for those of you watching the recording, please feel free to pause and think. Those of you who are not watching the recording or at the premiere, apologies, don't really have time to think. The answer to this is 3, 2, 1. These involve hydrogen bonds. Hydrogen bonds, hydrogen bonds. These can form different molecules between them will form hydrogen bonds. So when there's two molecules there and they've formed hydrogen bonds like intermolecularly, they sort of are able to stabilize a little bit better, even though it's not within their own molecule. You've got a little bit more stabilization, so there's less sort of that vibration. So if you think about it, NOF, remember the NOF rule, hydrogen with nitrogen, oxygen, fluorine. These have oxygens and these have nitrogens. Now, yes, these have oxygens and they'll be able to make hydrogen bonds with other, like there'll be hydrogens somewhere else in the molecule. So when there's two of them, correct, they will. But these ones are more directly involved. So that's why these three have sort of this higher wavelength, just a cool fact. So as you can see here, different bonds have different absorption characteristics and different changes in vibration, which we detect differently. So this is what it looks like. Now, what do you need to know about this? So the plot has sort of percentage transmittant versus the wave number. Don't worry about that too much. The wavelength is just a measure of the frequency, and it's just what you're going to use to compare with this. So you compare this with this along here. That is all you're going to use it for. Troughs are called peaks. So these are troughs, so these are peaks, peaks, peaks. These are all peaks. And these are where we detect vibration. So we've detected vibration there. Now, the other thing that's really important to know is the fingerprint region, which falls at around 1500 or below. Yeah. What do I mean by that? The fingerprint region is actually really, really useful, but it's beyond the scope of VCE chemistry. It's used in university level chemistry, and for those of you who do follow chemistry into university, you're going to see this a lot. However, for our level of chemistry, we don't look at it. It actually tells you about the individual characteristics of it. So I'll show you an example on the next slide, but the individual characteristics between molecules that are very similar, but they're slightly different. The fingerprint region is like its fingerprint. It's like, for example, if you have a twin, you and your twin look very similar, but your fingerprints are different. It's that characteristic that really, really determines the difference between the molecules. So molecules that are very similar, they're like twins to each other, but they're slightly different. The fingerprint region is the thing that determines them. So absorption in this region is characteristic of the molecule as a whole. Peaks above 1500 indicate the presence of particular bonds, which are really important. Pay attention to the intensity and sharpness and the shape of the bonds or bands. We're going to talk about these in a second. So as you can see here, these are two that have extremely similar functional groups and what's going on, but then look at their fingerprint regions. They're very, very different. These are different molecules. They're very, very similar, but they're different because of their fingerprint regions. So you're going to get this piece of information out of it. You're not going to worry about this. We don't worry about the fingerprint region. The fingerprint region is not relevant to us. We leave it alone. As you can see here, very similar. This is propane 1-ol, this is propane 2-ol. They're so similar. There's just that distinct OH in a slightly different spot, and you get a slightly different ion. So this is a very quick summary of the peaks that you sort of need to know, and we're going to go through examples for each of them. Or we're going to go through examples for like one or two of them. Actually, I'm going to go through examples for all of them, but we're going to go through examples for a couple of them. So these are the ones you need to know. So OH alcohols So this is when it's just an alcohol. You get a big, smooth, but intense, which means it goes all the way down to the bottom, peak at 3,300 centimeters. So it's a smooth and it's big. OH for acids, you get a big dirty peak, and we will show the difference between them, so don't worry. But it's just huge. It's a mess. It sort of engulfs multiple things. So the alcohol as well doesn't engulf. So what it means is that the peak is by itself, and then there'll be another peak next to it, and it sort of looks like a stiletto. So you'll see this one referred to as a stiletto, whereas acids are like a big peak, and they sort of absorb other peaks around it, and it's a bit ugly. CH, it's always a very thin, sharp peak at 3,000. It's not very useful. So most things will have a really sharp peak at 3,000. It's usually very thin. The acid will engulf this. The alcohol will not. That's a very distinct difference. So this engulfs this. This does not. The NH is an intense peak at 3,400, so it's a little bit further on. It doesn't really commonly come up. And then if you get a C double bonded to an O, it's usually a thin, very intense peak at 1,750. Now, there are loads of different things that have C double bonded to an O, so there are slight differences in them, but we don't really go over it in too much detail. It's just important to note that that's there. So, and as I said, it's not important to memorize numbers. It's roughly what you sort of expect them to be by looking at the shape. So, as you can see here, these are the ones that they all sort of look the same. As you can see this meme here. It's just trying to say that these ones all look very similar, and it's really tough to sort of determine between them. So don't expect to. Don't expect to be able to determine between them. You might be able to get a little bit of information out of it, but really, if you can just determine there's a C double bonded to an O, so a carbonyl group somewhere, we're good. That's really good if you can determine that, and you can move on from there. So, an example of propan-2-ol. As you can see here, propan-2-ol is an alcohol, and this is the stiletto shape. It's like this is the heel, and then this is the shoe. Like, it's a terrible, terrible drawing, but that is that sort of stiletto shape that we talk about. This is a really smooth peak usually. It's around 3,300, and it doesn't engulf that really thin CH bonding peak. Doesn't engulf that. It just has its own smoothness, and it's by itself. Now, if we go to a carboxylic acid, notice how, first of all, there's no peak here. This one, there's a peak here. That's telling me there's a carbonyl group. So there's a carbonyl group. That peak there is distinctly a carbonyl group. And then I have this really big, dirty bond that's, somewhere around 3,000, 3,100. I'm happy with that. It's a really dirty, big peak. This is going to be a carboxylic acid. And then lastly, we just have a carbonyl group here. As you can see, here's your CH. It's not very big. It's in this one here, it's actually not very intense, but you've got a CH. There's nothing else really here. This isn't big enough to be anything. There's nothing going on up here. But then you have a really strong, thin bond at about, that's just above 1,600. So being just above 1,600, you can say, all right, actually it's just above 1,700, apologies. That's definitely a carbonyl group. So you've got a carbonyl group there. In this case here, it's acetone, which is propan-1, because it's a ketone. And that's how you go about that. So as I said, IR spec, it's the first time you see it, it can be really confusing. And it's especially this. This is what confuses lots of students, but don't worry too much about this. You want to be able to determine this from this. You want to be able to determine that this is not one of these two. So comparing these three is really important. Being able to determine if it's just a CH or if it's one of these two. Being able to determine whether it's an acid or an alcohol. And then being able to determine whether there's just a carbonyl group. They are the three things I want you to be able to do. Now, you may get this, but this will just be very different. There'll be something really far along, and it won't look like either of these. And you'll be like, something's a bit different here. That's when it's a bit different. But the main three things I want you to be able to do is determine if it's one of these two or this, which of these two it is, if it is, and whether you've got a carbonyl group. They are the three things I want you to be able to determine with an infrared spectroscopy. It gives you the functional group. So you've already seen a mass spec, you've got the mass, you got the molar mass, and then you get the IR spec, you get a functional group. You'll be like, oh, I could nearly determine the molecule from here. But you may not be able to determine the exact sequence of it. Like, where are things in relative space to each other? So sort of like that three-dimensional thing we were talking about earlier. But in this case, we're like, all right, where does one fold fall compared to the other? And that's where you need your NMR. But out of this, mass spec, molar mass. Mass spec doesn't actually use EM radiation, so it's a bit weird that it's called a spectroscopy, but we still do. IR spec, vibrational energy states via IR or infrared radiation, and it's all about functional groups, and you need to know those three different ones, the three different things I want you to be able to determine. Then we move into NMR. So NMR stands for nuclear magnetic resonance. Now NMR uses radio waves, ultrasound and radio waves. NMR uses radio waves. Now NMR stands for, oh wait, for some reason there is a question and I've put the slide in the wrong spot. Whoops. Anyway, actually before we start NMR, we'll do this question. I don't know why I put the question after it, like 78, 79. I think it was meant to be on 78. I did put this question in and then completely forget to move it. I do apologize. Let's do this question. What type of molecule is this? That's all I want you to know. I don't want you to tell me what molecule is. I want you to tell me what type, what class of molecule, what homologous series does this belong to. This shouldn't take more than 15 seconds. So you've got 15 seconds in the top right. Those of you watching the recording, feel free to pause. You got 15 seconds, top right. All right, this is carboxylic acid because we've got a big dirty peak here. We've got a peak at about 1700. So this is about 3000. This is about 1700. This is a C double bond to an O. This is a this is your OH for your acid, but it's engulfed your CH bonding. So that is what's going on there. All right, now moving back. Sorry. NMR. So NMR stands for nucleic magnetic resonance. It's a very powerful technique. It's a very expensive technique to work through, but it's very useful. It yields information about structure and functional groups. So you can also get functional groups from this, but it just mainly tells you where the structure is. And it sort of tells you about the arrangement of things. Now, the basics. It uses radio waves. And so it's not high enough energy to change electronic or vibrational states, but it's exactly the right amount of energy to change spin states of nucleons. So what you're going to say for this is NMR uses radio waves to change the spin states of the nucleons, full stop. That's all you're going to write. That's your one sentence. So for IR spec, it was about IR radiation changes vibrational states, which can be detected. Here we're going to talk about radio waves change the spin states of nucleons, which can be detected. So it's just using what type of radiation is used, what changes to the molecule, and then it can be detected. It's as simple as that. Now, this affects carbon-13 and hydrogen-1. So these are the two things that it affects, and we're going to discuss this in a second. So, energy absorbed depends on the surrounding around the surrounding atoms, gives an important information molecules are connected. You know, it's like 2, 3, 1, 1, 2, 3, whatever it is. So, what's really important is just quickly to understand that radio waves are really low. They've got a really low amount of energy. So notice how infrared's got a decent amount of energy. Light, like it's less than light, but it's still a decent amount of energy. Radio waves is really, really small. They don't really have a lot of energy. So that's why it only changes spin states rather than, you know, going through everything else. Now, this is a slide on how it works. I'm not too worried about you guys, you know, understanding this. Feel free to read through it if you'd like. I'm just going to skip over it. So, NMR is super confusing to start with. In order to understand it, we need to first learn about a few different concepts. So please don't worry if today you don't understand NMR. It's just trying to give a brief overview. So, first of all, we'll start off with proton NMR because proton NMR, it sort of gives a little bit more information than your carbon NMR, and it's more useful, so we are going to go through it more often than your sort of, wait, I got them mixed up. Oh, we'll just go through proton NMR first. So proton NMR refers to hydrogen-1 NMR. It shows peaks as chemical shifts. So what you've got is this shift. So you've got 0, and then everything shifts across. Note that each peak sort of corresponds to a different area in your molecule. So notice how this is referring to this and this is referring to this. Now, proton NMR is far more useful. It's going to be the one that you cop more often. Now, there are splits here and there are, you know, different things in different spots. Why is that? So let's just discuss very briefly what's going on. So the number of peaks refers to the number of hydrogen environments. Now, what does that mean? These hydrogens are in a different environment to these hydrogens here, because this carbon is connected to different things. Now, if I gave you this molecule here, how many hydrogen environments are there? There's 2, because this hydrogen is connected to this carbon, is connected to a C2H5. This carbon is also connected to a C2H5 in the same order, and it looks the same. Now, this one is connected to 2 CH3s. It's a bit different, so therefore this one is a different environment. I should use a different color. This is a different environment, so there's 2 here. So it's really important to sort of be able to determine that. The peaks then split further, and this is determined by what's around it, and we will discuss this in a second. So let's look at sort of environments. So hydrogen atoms in the same environment are said to be equivalent. The number of environments equals the number of peaks on the spectrum. So you've got a molecule here, which is just ethane. How many hydrogen environments are there? Well, there's 1. All right, we're going to go through all of them. So how many hydrogen environments are there here? Well, if we look at this is identical to this. So there is 1 hydrogen environment. Well, that sun is really bright. I do apologize. Sun's decided to come out. And then if you look at this one here, how many have we got? Well, we've got 1 group and 1 group that are identical, and then this one here is different. So we've got 2. And then here we've got 1 hydrogen out here doing its own thing. This is very different. So therefore I'm going to say that is on its own. I'm going to say these 2 are the same because they are very similar. They come off, the same thing. This and then this are different. There's 1 here and it's coming off 2 CH3s. This one has 2 and it's coming off a carboxylic acid. So in this case here, we've got 1, 2, 3, we've got 4 different environments. So the number of peaks on the spectrum will be 4 for this one. Now, how many carbon and hydrogen environments do we see here? So let's go through hydrogen environments first, because that's what we've been discussing. So in our first one, we have 1, because these are all the same. They all come off the same thing, so it all looks the same. In our second one, how many are we going to have? We're going to have 2. In our third one, we're going to have, well, this one's a little bit different because you'd say this and this look the same, but what's really important is this one comes off an OH. This one comes off a CH2 with an OH. So this one is distinctly different to this one. So you're actually going to have 4 environments. Our last one here, we're going to have 2. Now, for carbons, it works sort of similar, but a little bit different. You look at sort of the surrounding things that come off it again. So if we go through carbons very quickly, carbons are less common. Carbon here, carbon environments, you've got 2 carbon environments because each of these are the same, but then this one is different. This one here, you will also have 2. This one here, you will have 3 because there are 3 different environments, and then this one here, you will have 2. So sometimes they match up. So as you can see, this one matched up, so hydrogen and carbon were the same. This one here, hydrogen and carbon were the same. However, over here, this one was different because hydrogen was 4 and carbon is 3. And then here, hydrogen was 1 and carbon was 2. So sometimes they're different, sometimes they're the same. You cannot assume that they're always going to be the same. Now, the other cool thing here is how do you determine between carbon NMR and hydrogen NMR? Hydrogen NMR has splits. It has these splits. Their peaks split up. Carbon NMR does not. Carbon NMR is just single lines. Now, the other thing about this as well, carbon NMR goes up to a really high number. Hydrogen NMR does not. It usually goes up, sometimes it goes to 10 or 20, but it usually stays pretty low. Hydrogen NMR is more useful on the other reason is that you can get these splits. Now, these splits are determined by this really cool thing called hydrogens, like neighboring hydrogens. So what that means is, I'm going to use this example here because this is a really good example. In this environment here, so this is environment 1. Environment 1 neighbors with environment 2. So this is environment 2, it neighbors with it. If there was a carbon in the middle with no hydrogens coming off it, for example, it would not neighbor because there's something in between it. But in this case here, there's nothing in the middle, so it neighbors with a carbon with 2 hydrogens on it. So it neighbors with that other hydrogen environment. So how many peaks is this going to have? How many splits is this going to have? Well, it's going to have neighboring hydrogen plus 1. So the neighboring hydrogens was 1, 2. So because it has 2 hydrogens in its environment, it's going to be 2 plus 1. It's going to split into 3, and it has 1, 2, 3. 4. Now, other one over here for our environment number 2, it's going to split of NH plus 1, so neighboring hydrogens plus 1. Neighboring hydrogens is 1, 2, 3, so it's going to be 3 plus 1, which is 4, and it's split into 4. So that's how that works there. So hydrogen does that, carbon does not do that, really important. Now, in the other case here that we drew before, is this one here. Now this has one environment. It's got this as one environment and this is the same environment. So how does this split? Trick question. It doesn't split. This has no splitting ability at all because these are the same environment. As much as they are like, you know, they're separate, they are the same environment. There's no difference between them. And because they are the same environment, there's no ability to split. So that's not neighboring. Those hydrogens are technically not neighboring hydrogens because we refer to them as the same. They're in the same house if you think about it. So there's no splitting here. Same with some of the examples here. This hydrogen is not going to split. Now, you might ask, why is that? Well, there is an oxygen in between the carbon here. So this hydrogen is working off this oxygen. It's a bit of a different one. This is not going to split. This one here would split into 3 because there's 2 here. This one here would split into 6 because there are 5. There's 3 and there's 2. This one here would also split into 3. So that's where this splitting comes into it, and you can sort of figure out by looking at the splits how you can determine what's going on with your molecule. So things are always a little bit different. This one here is also really cool because it splits into 7. It splits into 7 because there are 6. They may be the same, but there are 6 hydrogens that are in different environments to him. So there's 6, and then splits into 7. So, I think that's just a summary of it. Just a bit of a summary of NMR. So let's just briefly go through a question. Like I don't expect all of you to do this. You're welcome to pause now if you'd want to. Those who are at the Premier, you don't get an option. I'm just going to go through this. So what you've got is, this is an ATAR Notes Practice exam from 2019. And we have a bunch of graphs. So it says a chemical that contains carbon, oxygen, hydrogen. So it's got carbon. It's got 3 carbons to 8 hydrogens to 1 oxygen, and that's just the ratio. So I could have 6, 16, and 2, or I could have 12, 24, and 3. So that's just the ratio that's going on there. Not 12, sorry, it'd be 9. I don't know why I said 12, it should be 9. That's just the ratio. So that is just the ratio there, but that's what we've been told. That's the molar mass, the molecular formula ratio. So looking at this, what have we got? So first of all, A, the infrared spectrum is shown below. In the table, write the bond responsible for the given wavelength. So the one at 3,325, so the one that's there, that big smooth bond, what do we think? It's going to be an OH alcohol. Really important you put the alcohol in brackets because you don't want to write OH and assume it's a carboxylic acid. Now, what is the bond at 2,962? Well, this is going to be CH. Cool. Moving on, B. The mass spec of the compound is shown below. Write the mass to charge ratio of the base peak. Well, the base peak is your biggest peak. So it's going to be at 1, 2, 3, 4, 5. So 45 mZ. Now, what else can I tell from this? It hasn't been asked in the question, but what else can I tell? What is the molar mass? Well, it's either going to be 59 or 60, I assume. 60 is probably more going to be the answer. So I'm going to write 60 as my my parent molecular ion. Now, that wasn't asked in the question, so it's not relevant to the question, but for me, that's useful. So moving on, what have I got so far? I've got that it's an alcohol, and I've got that it has a molar mass of 60. That's what I know so far. So then it says, draw the 2 possible structures for this molecule. Well, 60 if I do this, this is 36 plus 16 is 52 plus 8 is 60. So it's going to be this. It's going to be C3H8O. So, and I know it's an alcohol. So what are the two possibilities? Well, if I have 3 carbons, what are the two possibilities? Well, it's either an OH here or it's an OH on the start. And then these are the other molecules. All right, moving on to C. So I've got propane 1-ol and propane 2-ol are my 2 options, by the way. So moving on to it's given me carbon NMR here. It hasn't given me hydrogen, it's given me carbon, so a little bit different. Carbon NMR. What do the following peaks tell me? Now, we didn't go through this in too much detail because I didn't want to go through it and confuse you all, but you can find this here. So this is figure 15 and figure 16. Now, figure 16 is far more useful because hydrogen NMR is far more common. Notice how it tells you all the chemical shifts. It tells you what hydrogens it's referring to in bold, and there's loads. It goes all the way down to 13. So this is what this is telling you. And it's telling you where the chemical shift is. Same here for carbon. So it's the carbon that is put in there. They didn't bold it because there's not extra hydrogens around. As you can see here, these are that. Now, what's also really important is sometimes you'll get a peak at 0, and we haven't discussed this either. The peak at 0 is TMS. It's a standard. It's what it's used to just compare with. But what we've got here is we've got 1, 2, 3, and it wants me to talk about the peak at 64 and 25. Well, what are the peaks at 64 and 25? Well, the peak at 64 is probably going to be this here. Probably makes sense. So this is going to be RCH2OH, and then my peak at 25 is going to be looking at this. Oh, you can't see what I'm writing, but that's what I wrote. And then looking at this, it's probably going to be, I'd say, probably this is probably your best, or maybe even this. I'd say it's probably this. I'm going to say it's that. So RCH2R, and it would make sense because it's probably fitting into this molecule here. So name the compound that's consistent with it. Well, it's going to be propane 1-ol. And then what is the purpose of the TMS peak and ethanol, What is the complete combustion? I'm going to leave these questions to you. Oh, sorry, you couldn't see that because I had that up. I'm going to leave these questions to you. You're welcome to have a look at them if you'd like. What is the purpose of TMS peak? It's used as a standard, and then you can go through and do the second part there. But that is an example of how you use all your information in a question and an analytical question. This is a pretty straightforward one, but it's a good one to sort of start off on. Nonetheless, that is analytical chem. There's also like volumetric analysis. You're welcome to have a look at it. That's titrations. You guys need to go through that yourselves. This is year 11 stuff, so you can go through year 11 notes and have a look at it. We are out of time for today, so I'm not going to bother going over it. So that's a summary of what we went through. We really just went through this. There are slides on this, and you do need to go over this yourself, particularly this here. They are important to revise and important to make sure you understand prior to sort of going into any sort of 3-4 sort of exams or, you know, all of that stuff. So nonetheless, that is everything for today. So just to summarize, we've gone through pretty much all of or most of area of study 1 of unit 4. So as you can see, we've gone through all of this and most of this, not all of it, but most of it. And we've gone very briefly over this. So realistically, we've really done half in detail and half very briefly. This is really important to sort of get your head around. And it's really important to sort of take some notes, have some very brief notes from today. So then when you see it in class, you'll be much better for it. You'll be able to get your head around it really quickly and you'll feel far more comfortable. Otherwise, I'm going to leave you all to it. Please enjoy the rest of your day. Please make sure you get around all of the ATAR notes, content, the free, and any of our promotions that are down below. I'd like to thank our sponsors, which you'll be able to see down below as well. Otherwise, go and enjoy your day, and hopefully I'll see you again for our spring lectures, which will be more of a revision of Unit 4 and more of an exam-ready style lecture, which will be more exciting because you'll be nearing the end then. Otherwise, good luck, and I'll see you all around.